Hi, my name is Jake Scher. I'm a graduating senior. I just got done taking ECE 422 with Dr. Zhang, Microcontrollers Design, 3-credit course. I'm going to show you a little bit about the final project, what we've been working on in the last few weeks. It consists of the portal board here. You can see we have a PICC 18 from Microcontroller, LCD, USB interface, and a keypad, along with some buttons and dials here that I'll be showing you more about later. We have some code written in C# for our GUI. Again, I'll be showing you that later. And the code on the microcontroller was written in C using CCS. Alright, so first a little bit about the GUI written in C#. You can see we have our voltage display up here. That's time domain representation. We have our frequency domain representation down here. We have options to either take the fast Fourier transform or the discrete Fourier transform. You'll be able to see later that the fast Fourier transform is indeed a lot faster. We can plot both the signal and the spectrum, or just one or the other. Sometimes you don't care about one or the other, so you can speed it up a little bit by only plotting one. We have a single button. What that will do is send the trigger value to the PICC, and the PICC will wait for that value and then only display, like if you want to look at a button to bounce or something like that. Run, stop, 4 channel selects, and also 3 measure buttons. We can measure the temperature in the room, we can measure the pulse width of the signal being currently measured, and we can also measure external capacitances based on rise time. Well, I'll show that to you later. So right now the PICC's all connected. If it wasn't connected, you could pull up these port settings, change any of the port settings. Right now I'm running it through USB and USB serial port emulation. So it pulls power, everything straight from USB. Don't have to worry about external power supplies. So we can go ahead and run it here. You can see we got a square wave coming in right now. Pretty fast. Let's switch it over to a sine wave. You can see that. So trigger value, you can see it's plotting right from that trigger value. We can crank it up, crank it down, and it'll always plot right from that rising edge. Automatically calculates frequency, period, peak-to-peak voltage, and average voltage, kind of the 4 important measurements when you're just looking at a signal. So we can crank it up. You can see that the spectrum works up to pretty high values. So the time domain has already started aliasing, but the frequency domain still works. Right now we're sampling at about 14 microseconds, the maximum on the PICC 18. So it'll work all the way up to about 35 kilohertz. And we can crank it back down, and you can see even though it's starting to alias there, it's still pulling a decent frequency measurement out of it. So I'm at 12 kilohertz right now in the function generator, and we're measuring in between 11.9 and 12.1, so pretty close. You can see the voltage peak to peak. We can change offsets, we can change amplitudes. All that works just fine. Basically the only drawback to this compared to a normal oscilloscope is this has a 0 to 5 volt range, because that's the power supply on the PICC. You can go a little bit above that and it'll be alright. It won't, but any more than about a half volt above or below 0 to 5 volts, it'll reset the PICC because that's outside the range. So a little speed demonstration. You can see right now it's updating pretty fast. I can crank on the knob on the function generator and it updates it pretty fast. But when I go to DFT, just a normal discrete Fourier transform, you can see it's acceptable, but it's a lot slower. So back to the FFT, you can see it keeps up much better. One interesting thing, you can go to a triangle wave. You can see the little harmonics in there. Something that's very useful. So let's show some of the measuring stuff. So we can click on measure temperature. Right now, no interruption in display. It automatically just sends it out to the PICC. PICC sends it back as fast as it can. It's 74 degrees Fahrenheit in here right now. We can go to square wave and measure pulse width. So we can click on measure pulse width. And since we messed around with the offsets, we got to get it back down. Right now this is going to use the compare and capture mode and find a rising edge and falling edge based on logic 1 and 0. So it has to make sure to go above and below that. So now we're above and below that. You see we got 0.34 milliseconds, 0.34 milliseconds, and a duty cycle of 50%, what we expect. Unfortunately, this is an older function generator. I can't change the duty cycle, but trust me, it works just fine. Also, we can measure capacitance. What this does is it sets an output pin on the microcontroller high, and then waits for the voltage to come up to 63% of its maximum, which is 5 volts. And that will then tell us the time constant associated with that resistor and capacitor pair that I have on there. Then using math, it'll work backwards and find the capacitance value. So right now I have a 10 microfarad hooked up to it. It measures 10. Let's drop it down a little bit. Have a 0.01 microfarad hooked up to it. Measures 0.0104, so pretty accurate. And we can drop it all the way down to 0.001 microfarads and measures 0.0012. So pretty accurate for a little $5 pick. One other cool thing is change channels. So right now channel 2, that's the channel I have the temperature sensor hooked up to right now, so you can see it's low. Channel 3, that's just a little potentiometer I've hooked up to it, so you can crank the value on the potentiometer and it changes, it goes high or low. And channel 4, I just have a button hooked up to it, so I don't know if my camera can catch it, but right now it's high, push the button, now it's low. So if we wanted to do a single capture, we can leave it high, click on single, and as soon as I click the button, boop, sees right there the voltage drop. Once it crosses this trigger, it keeps the previous value, 256 values, and sends the newest 256 values. So the total sample is 512 8-bit values. And we can do the same from high to low. So right now we're low, so we can click on single and let go of it, and you can see it's low, captures that rising edge, and then waits for it to come. We can also do the same with the function generator. So right now we'll click run, go back to channel 1, which is our oscilloscope. In our function generator, I'll disconnect it. So right there, it looks like it turns on right away, but there's some transient involved. So we can click on single, and then I'm going to pop it down, and you can see, boom, right there it starts. So this has been the final project for 422 GUI interface. Now let's look at some of the PICC code. Right now, so we're still running on the code. So if I hit button 1, channel 1 selected, channel 2, channel 3, channel 4. When I hit the 5 button on the keypad, it's going to clear the LCD, anything that was on there. So we can go back to there. You can see channel 2. I'm going to hit 5, clears the LCD. Likewise, if I hit 6, it'll automatically clear everything on the GUI screen. If I hit 7, it's going to go ahead and measure temperature. If I hit 8, it's going to try to measure pulse width. Right now we still have the same square wave coming in here, so it's going to be 50%. And then if I hit 6, it's going to measure capacitor. So right now we're on this little 0.1, and we can move it over to the 10, hit 9 again. It's going to measure cap. Now we're on 10 microfarads. And then I believe this is a 0.47. I could be wrong. Yep, that was the 1 microfarad. This should be the 0.47. There we go, yep, measured 0.48. So, that's a little bit about on the breadboard side. You can see here we have a reset switch and then a bootloader switch. I'm running a USB bootloader, so you don't need to program the chip with anything like an in-circuit debugger or anything. Simply hold down this button and then click the reset button at the same time. And now we're in the bootloader, so we can just using like a hyperterminal or in CCS, there's a built-in function. We can just automatically send over our program and program it right to the PICC and not have to worry about any sort of in-circuit debugger or anything. And then a little power switch, and everything's off and good to go. Like I said before, everything's powered off of a USB port, no external power supply needed, so it's handy, all in one package. So 422 was a great class, very hands-off, kind of let you run with it if you wanted to and if you had the time to. As you can see, great things are possible. It was really amazing to me that the microcontroller is literally a $5 microcontroller, but it's so powerful and so capable. And there's resources out there, and Dr. Zhang is very approachable if you need any help. So I would highly recommend this class. In the 3 credits of this class, I think I learned more than a lot of other classes that have been either equal or more credits. So I'd like to thank Dr. Zhang, thanks St. Cloud State University, and see you later.